Here we are going to introduce the integral test. The integral test is a method used to determine if a series converges or diverges. So we start out by talking about f, which is a function, and we say, okay, if f is positive, continuous, and decreasing for all x greater than or equal to 1, and my formula for the a sub n's can be rewritten as f of n, then the series represented by the sum n goes from 1 to infinity of the a sub n's and the integral from 1 to infinity of f of x dx either both converge or both diverge. So to be able to use the integral test, I have to first verify that my function meets the requirements. And I do this by making sure that the function is positive, continuous, and decreasing. Okay, so let's take a look at some examples as to how to use the integral test. So the directions for my examples are: confirm that the integral test can be confirm that the integral test can be applied to the series, then use the integral test to determine the convergence or divergence of the series. So these are from my course, my Calc 2 course. This would be number 6 on page 622. So we're asked to determine if this series converges or diverges. So for this series, we would see that f of x, my function, would be x times e to the negative x over 2. So we see that f is positive and continuous because x goes from 1 to infinity. And it's decreasing because this e to the x over 2 actually goes in the denominator. And it grows much faster than the x that would be in the numerator. And we'll show later a better way to demonstrate that. So if I'm using the integral test, this is the integral that I will be taking. Okay, so I have the integral from 1 to infinity of x e to the negative x over 2 dx. So I have to rewrite it as an indefinite integral. So I take out the infinity and put in the limit as b approaches infinity of the integral from 1 to b of x e to the negative x over 2 dx. And of course, we recognize right away that we're going to be using integration by parts. And we're going to say that u is going to be x and dv is going to be e to the negative x over 2 dx. So now I have to find du and v, as you see here. And then I go ahead and apply my integration by parts, and here's what I now have. The limit as b goes to infinity of negative 2x e to the negative x over 2 minus the integral as b the integral from 1 to b of negative 2 e to the negative x over 2 dx. Well, we basically did that integral right here. So we end up with the limit as b goes to infinity of negative 2x e to the negative x over 2 plus negative 4 e to the negative x over 2. And it goes from, evaluated from 1 to b. So I make my substitution. Here, these become constants. And here I have terms involving b. So what I'm going to do is let b go to infinity, and what happens is these pieces all go to 0 because this e term goes in the denominator. So these two go to 0, and I'm left with negative of these two put together, and I end up with 6e to the negative 1/2. So my series converges. Let's move on to the next problem. Let's take a look at number 22 on that same page. So number 22, we're doing the same thing. We want to determine if the series converges and can we use the integral test. Well, here we see that f of x, my function, can be written as x over x to the 4th plus 1. So then, by inspection, we see that it's positive because I'm using values for x from 1 to infinity, and it's continuous because the denominator is never 0. But let's take a look at how to show it's decreasing. Well, we can do that by taking the derivative of f of x and verifying that f prime is going to be less than 0 or negative, which means it's decreasing for all x. So I'm going to go ahead and take that derivative, and of course, we have to use the quotient rule. So I take the derivative of the top times the bottom, minus the top times the derivative of the bottom, and divide it by the denominator squared. So here's what I end up with. I'm going to go ahead and simplify that. And here we see we have the derivative is negative 3x to the 4th plus 1 divided by the quantity x to the 4th plus 1 squared. Well, that's going to be negative for all x in the interval 1 to infinity. So we're good. That means it's decreasing, and we can go ahead and use the integral test. So now we go ahead and set it up for the integral test. There's my integral using my f of x, the original f of x. And we kind of recognize this as possibly being arctangent. So let's try forcing it to look like the integral that will give us arctangent as an answer. So we're going to let u equal x squared. So then du equals 2x dx. And to make my substitution, I see I have x dx, so I need 1/2 du. So I go ahead and make that substitution and rewrite it as in indefinite integral. And I have the limit as b goes to infinity. I'm going to throw that 1/2 out front, and I have 1 over u squared plus u du. Well, that is arctangent. So I end up with the limit as b goes to infinity of 1/2 arctangent of u, because that integral, the answer to that integral is arctangent of u. And I'm going to evaluate from x equals 1 to b. Well, I got to substitute back in x, which gives me the limit as b goes into, oh, well, that would help if I move that up for you guys. There we go. And then we have the limit as b goes to infinity of 1/2 arctangent x squared evaluated from 1 to x, and 1 to b. So I'm going to make that substitution. Let me organize this a little bit here, straighten it out. And you see that I have 1/2 arctangent b squared minus 1/2 arctangent of 1. Well, we know the arctangent of 1 is pi over 4. So this piece right here is going to be 1/2 pi over 4 or pi over 8. Now, let's think about arctangent. If you remember the graph of arctangent, here I've drawn it, and it's basically the inverse trig function for tangent. We know that the domain can go to infinity, but as x goes to infinity, y approaches pi over 2. So then, from that little review there, we know that these two are going to evaluate this way. 1/2 times pi over 2 minus 1/2 times pi over 4, which gives us a final answer of pi over 8. Since the integral converge, then so does the series. And that is how you use the integral test to prove a series convergent and find out where it converges to.